Okay, good afternoon, everybody. I hope everyone's having a wonderful day. I want to kind of take us back to where we were last time. So, just as a reminder, remember that you still have some time for the first assignment, but I recommend getting started if you have not already. But other than that, how's everybody doing? Is everything going well? Okay, it sounds like everything's going well. So what I want to do today is I want to revisit back to what we were talking about last time, and then I'm going to be transitioning to one thing I would consider one of the most important building blocks of this class. So I don't want to spoil it quite yet. But I want to first, before we do that, I want to talk about another example of designing another NFA. You may find this one relevant for your assignment. So what I want to do is I want to have it so, suppose I give you an alphabet with C, A, and T in it, and I want to design an NFA that will accept strings if they have cat or tack in them. So for example, it could be like cat tack. It could be CCAT like this with another T after it. It may have both of them like this. The point is it has to have cat or tack in it. It can have both of them as long as it has at least one of them in it. So I want to design an NFA to do this. Now, I want your help to help me design it. So the first thing I would want to start off with is I'm going to make a starting state. Now, I'm going to take advantage of a little technique that you'll find I'll give you an actual application that you could use this technique for. But I want you to think about this. Okay, I'm going to go back to when we were designing DFAs. Do you remember what I did when I did design a DFA that accepted a substring of a given sequence? What did I do? Can somebody tell me? What did I do? I kind of drew it out for you, right? So can somebody give me an idea of, say for example, I only want this thing to accept cat. What would be the thing I would do? Somebody tell me? Just cat. Just tell me what I would do with cat. Yeah, that's basically what I'm thinking of. Is that you would have a C, an A, and a T like this. And ideally, this would be your final state, right? So you would have something along this line. So imagine I have, so I'm going to label this Q1. We'll call this Q3 because I'm going to add some more states later. Q5, but that's exactly what I was thinking about. Now, remember, we also want this so that it will accept symbols before the cat appears. So imagine I have like A, C, C, C. So what was the trick that I showed you last time, what we did with NFAs to allow this to happen? So how do I permit more guesses from happening with the NFA? Yeah, self loop. We're going to put a self loop here. I'm going to allow it to take on any one of alpha. Sorry, of sigma. Getting a little ahead of myself. So I'm going to pick a self loop. I'm going to put transitions on CAT so that if I read any symbols, yeah, good, I see in the chat too. I'm just going to allow it to stay in Q0 in case if it did encounter something like imagine if it read ACCA like this. You'll notice that it will keep a state in Q0. As soon as it sees a C, it will be in Q0 and in Q1. It sees a C again, it won't transition anywhere on here. That thread is basically gone. So I'm still back in Q0, but I read a C, so I go back over here, and I also have here as well. I read an A, this one in Q1 would go to Q3. There'll still be one in Q0 in case there's nothing here, right? And if there's nothing here, it'll stay in Q0, right? There'll be a state there. Now, that's the first part. What do I do with, so suppose I read cat like this. What do I need over here to ensure that if there are more symbols after I see cat, how do I deal with that? See, I hear the idea of a garbage state. Now, believe it or not, I don't need a garbage state because ultimately, remember, any symbols I have after I read cat, they don't matter, right? As long as I read cat, I'm okay. So if my goal is to stay in Q5 when I'm in the final state, after I read cat, maybe I should use what? But the garbage state is a great guess, by the way. Yeah, the self loop. So I'm going to put a self loop here, and I'll put CAT like this. So now notice now, this will require me to see CAT to get to Q5. But as soon as I see CAT, I'm allowed to take in any more symbols as I like. So this will allow me to accept strings containing cat. Does anybody see all I have to do to modify this to allow me to have tack? Does anybody see any ideas what I can do? I'll give you a hint. The way I numbered the states should give you a hint of what I'm going to do. Yeah, add 2 more states. So I'm going to add 2 more states. Q2, Q4, perfect. And what should I do? What should I do? Perfect. And then I go Q2 to Q4, right? And then I can go like this, right? Perfect. Perfect. Right on the nose. I love it. I love it. Wonderful job. So now notice all I had to do to modify this idea was just add another path. So now notice I have a path from Q0 to Q5, but now I use these symbols instead of cat. So now I have tack and cat. So do you see how with the NFA, this actually makes designing something that could recognize certain keywords really nifty. So you can actually quite easily see how this would accept cat or tack. I just follow a path, right? Now, later on, I'm going to show you a more versatile way of doing this. But notice that what I've just described here, first, before anything, does everybody understand this transition diagram? Is everybody okay with this? Just don't hesitate to stop me. So I'm mad with power. So anyways, the big thing is that notice that I can recognize keywords using this technique. So there's an easy application for this design technique is for recognizing keywords or key phrases. So notice that if I wanted to add more key phrases, all I'd have to do is add another path like this, and like this, and like this, and I would use the exact same idea, right? So notice the idea is very easy to extend, but notice that isn't this kind of neat? So you have a very simple way of designing a machine that could recognize keywords. Now, you might ask, Dan, well, this is still an NFA. Well, of course you could describe an NFA. Of course you could conceivably build one of these things, yes, but it's something that you would want to some way of translating this into something a little easier to work with, like a DFA, right? I don't want to get too ahead of myself, but I'll tell you that there is some way of doing this. So is everybody okay with this example? So I just want to motivate that, yes, the NFA isn't this strange abstract thing. You can actually use the design of an NFA to recognize and design very simple keyword or key phrase checkers. But we need some way of thinking about this in terms of exactly one state. Otherwise, we're going to have to keep track of so many of these states and it's a giant pain in the butt. So that brings me to my next point. So I have a question for you. So up to this point, and I think earlier on when we first started talking about non-determinism, and keep in mind, I'm talking about a very simple kind of non-determinism when I'm talking about an NFA. The question is, because remember, I've been designing NFAs, and they do all these lovely things like recognizing keywords and key phrases. I can use them to do that. Is there, a fundamental question is, is the NFA, this model, more powerful than the DFA? Is there a language that I can design an NFA for that I can't design for a DFA? So that's going to be the next fundamental question we're going to look at. So we're going to first see our first example where we're going to determine whether it is that one machine is indeed more powerful than another machine. So that's why I'm saying this is an important step. So let me move over here, and I'm going to spoil it for you because I need to really make sure we're all on the same page what we're going to be doing next. So what I'm going to do is I'm going to show you that, in fact, this is going to sound a little strange at first because remember, the NFA has all sorts of neat things it can do, right? It can transition to nothing. It can, for example, it could transition to a set of states, not just one. So at the first face of this, it sounds a little strange, right? Because shouldn't it be that like, oh yeah, I added all these new features. It should be the case that the NFA should be more powerful than the DFA, meaning it could recognize more languages. But what I'm here to tell you, and this is both exciting but also surprising, is that no, actually all the languages an NFA can recognize are regular as well. So implying that for any NFA, there exists a DFA that accepts the same language. So what we're going to do today is we're going to prove this fact. And I'm going to use at its heart this idea called the subset construction. Sometimes in some communities they call it the power set construction. Both names, they make sense within what we're doing. I'll try to emphasize that difference of why some people call it one way and other people call it the other way. But I want to give you an overview for what we're going to do. And this idea is going to be something we're going to use plenty of times in this class. So I want to make sure you get cozy with this idea. That I can take a machine, transform it into another machine by building another one, and then I can show you that that machine is capable as the other one. So what we're going to do is imagine, so the first part of this is the subset construction. The idea is that I'm going to give you any NFA. I'm going to show you the subset construction that lets you build a DFA from the NFA. So meaning that I could take any NFA and I could build a DFA. And then I'm going to show you the other direction, or if I give you some DFA, I can show you that there's an NFA. So everybody understand the idea? So I'm going to show you how you build one from the other and vice versa. Believe it or not, one direction of this is much easier than the other one. So we're going to actually have to prove something here today, not just justify things. Is everybody clear with this? Are we all good with this idea? So I'm going to describe next the subset construction for you. So this is the thing that people are asking me about. So are we all good? Everybody understand the game plan? I'm going to show you the subset construction. I'm going to then prove that the subsets, yes. Yes, so what's going to happen is I'm giving you an algorithm to create. So if I give you the description of an NFA, that this subset construction, which is going to be a construction or procedure, it's going to take the description of the NFA, and we're going to use that to build a DFA. And now this part here, it says slightly modify the DFA to the definition of an NFA. This part's going to be much simpler. Depending on how much time we have, I'll probably let you just read it. It's actually quite nice and simple. Because like I said, determinism is a special case of non-determinism. So you're going to see an example of that. So does that clarify anything? Okay. So I'm going to proceed. We're going to talk about the subset construction. And we're going to see some examples. And I'm going to show you a variant of this called the lazy subset construction. This is the one that, honestly, if you're going to do this, I'd recommend it. It's also something rather nice to implement if you needed to implement it. Okay, so let's talk about the subset construction. So what I'm going to do is I'm going to describe the process to you in terms of how we construct the DFA. So let's talk about the subset construction. Subset construction. So I'm going to be given NFA and it's going to be given a set of states Qn, sigma, delta n, Q0, and Fn like this. We describe or construct a DFA. Construct a DFA D, which is going to be equal to QD sigma delta D Q0 and FD, where L of n, the language that is recognized by n, is equal to the language recognized by D. So construct D as follows. So before I get too ahead of myself, I really want to warn you of one thing. With this construction, you're going to see quite quickly that when we build the DFA, you'll notice right here that I'm describing the state as a set. Notice that this looks like a set right now, right? But I want to warn you that when I write this, this is actually a label for a state. This is a label for a state. I want to warn you about that. So the great thing is that after this construction, if you really don't like these labels, they look kind of tacky looking, you can always relabel them to be whatever you like. But just be aware of that fact, is that this is actually a state. We're just using it as a name. However, when we actually talk about the NFA, that's actually a set of states. Does everybody understand the difference? Because this is going to matter when we get there. So you'll see the difference in a moment. So first I'm going to describe how you build the states. So QD is the power set of Qn. If you're not sure what that is, remember we talked about this. It is all the subsets of Q of Qn. So this is what I mean by labels. So what's going to happen is each one of the states in QD is going to be representing a subset of Qn. So, and each one of them is going to look like a label. So just as a warning, and this is actually why some people call this the power set construction, because look, it's right there. It's right there. Or if you think of it subset construction, it's all the subsets. So that's where the name comes from. So just as a remark, if there are n states in N, there are how many states in D then? How many states would be in D if N has n states? How many states would D have if it's the power set of Qn for the states? So if I give you n states, how many states will there be when I look at D? 2 to the power of n. It's 2 to the power n because it's the power set of Qn. And remember, that's the cardinality of the power set given a finite set with n elements. That's where it comes from. There are 2 to the power n states in D. This comes back to that idea, somebody mentioned it earlier on in the class about exhaustive. This is where that intuition really pays off. So now I must note, and this is going to come up later, note that any states in this construction, not reachable or accessible by or from the start state from the start state can be discarded. So if you're thinking about this, okay, Dan, well, there could be 2 then states. It's worth noting that this intuition for a lot of the examples you're going to see is not actually going to be the case. If you really just want a DFA that does what it says it does. In reality, what happens is that there's going to be very often states that you will never be reachable. And I mean that in the graph theoretic sense. As in, like, if you have a start state and you think of this as a directed graph, there's going to be some states that never could be reached from the start state. Another way you could say this is that there is going to be some states possibly that are never going to be accessible from the start state. These you can delete or remove from your DFA. And in fact, many times you're going to find that the number of states is not even anywhere close to 2 to the power of n. Later, I'm going to give you a so-called lazy subset construction, and that one will actually build such a DFA that won't have any of these extra states that are not accessible from the start state. Why am I not describing that now? It's because you need to know what subset construction does first. Okay, that's all I have to say about the states. So the final states. So how do we get the final states? So FD is all subsets of the states of n that include at least one of the final states of n. At least one of the final states of n. To be more precise or exact, I'm going to write this out exactly, if that isn't clear. Okay, so more exactly, FD is the set of sets or subsets S of Qn so that S intersect F does not, actually should be Fn, is not empty. So what this is going to mean, now remember I told you that in the DFA, we're going to have all of the subsets as states. Some of them are going to have states within those subsets that are going to be the final states. What I'm saying is you're going to label those ones as final states in FD here. You'll see when we get to the example, this is actually quite a simple step. Is this clear, everybody? Because I'm going to talk about what a transition is in this. So I'm going to talk about transitions, and then I believe I've described everything to you, because the start state is described as up there. The alphabet doesn't change at all. So all we have to the left is to talk about delta D. So I'm going to say for each subset S, which is a subset of Qn, and each input symbol A, which is one of the input symbols, what we're going to do, now this is going to look a little ominous at first, but I assure you there is a plain and easy way to understand what I'm going to write here. Delta D of SA. This should look a lot like how I built the NFA transition function. So I'm going to have delta D of that subset given the symbol A is going to be the union of each P in S of delta N of PA. So what I'm going to do is I take each one of the subsets and for each input symbol, I look at that subset, I read what the symbol tells me, and then I look at every one of the every one of the states in that subset, and I apply the transition function on that symbol on that state given that symbol. So in plain language, all you do is you look at all the states P in the subset S, and then all you do is you union together all the states of N so that go from P to whatever transition that is on that symbol A. I assure you this is going to seem a lot simpler once we get to the example. This looks a little ominous at first, but I assure you it's not too bad. And that's all of the subset construction is. Are we okay with this so far? Once we get to the example, a lot of this is going to look a lot less cryptic. So I'm going to proceed to an example. I think that will help a lot more with understanding this process. So let me just do an example with you. You're going to see that I'm just going to plow right through this and describe a DFA for you quite quickly. But you're going to see that it's going to take a little while because I'm going to have to go through every single one of the subsets of my NFA. Okay. So let's do an example. I want to make sure that you see at least one of these. I'm going to consider the following NFA. So Q0, it's just going to have transitions on 0, 1, a self loop like this. And then I'm going to have a 1. This looks like the same one I did last time, except I removed the loop on the end. This one's in the notes. It's a modified version of the one we did from last day. So I'm going to take this NFA and I'm going to apply the subset construction to it to build a DFA. So what I have to do, if you think about it, okay, well, I got to describe everything to you. So I'm going to do this as a transition table. I find that doing this with a transition table is a lot quicker, unless you really have a mind for graphs. So what I need to do is I need to list all the subsets on this side. So I'm going to have a row for each subset. So I'm going to start off with the empty set. I'm going to have a subset for Q0. I'm going to have a subset for Q1, a subset for Q2. Like I said, you're going to be drawing a lot of curly braces, man. Q0, Q1, Q0, Q2, Q1, Q2. All I'm doing is labeling all the subsets of these states, right? That's what I said over there. And then I'm going to have Q0, Q1, and Q2. So now all I have to do is fill in this table. Now, one thing I'll look a little strange to at first is that we actually have a state named the empty set. That is a thing you'll have to get used to. And so now remember, and everybody, so let's see, we got 1, 2, 3, 4, we have 8 states. There are 3 here. So 2 to the power of 3 is 8. So we have the power set right here. So this is all possible subsets of the states of my NFA described up here. So is everybody fine with this so far? I'm going to next label the start state. Remember, Q0 is the start state. So I'm going to just label. And now remember, I really just need to stress this again. These are the names for the states in our DFA. They're labels. But in the NFA, we treat these as actual sets. So that's the start state. Now we need to label the final states. It's whichever ones contain Q2. So look at that. There's Q2 right there. So that's a final state. Q2 is in this subset, so I better label that as a final state. Q2 is in there, and Q2 is here. So all 4 of these are final states. So are we doing okay so far? Give me 2 thumbs up. I need to know. Because we're going to be doing the trickiest part here. And you're going to find that this is going to feel like I'm doing some exhaustive process. Okay, good. It's going to feel like I'm doing some process. It's going to seem very exhaustive. This is why I'm going to show you the easy version after this. Okay, so you got to interpret this like a set when I feed it to the NFA. So I want to think about the transitions on the NFA. So if I have no states and I read a 0, there's no states to transition to, so it's empty. And when I read a 1, there's no states here, so there's nothing to transition to. Hence, this will end up being actually what we described earlier today, a dead state. So this is a dead state right here. So now what we do, now this is where things are going to get fun for us. Okay, so all I'm going to do is I'm going to look at, so I look at all the elements in this subset. This is what S was over there in the transition description. So all I'm going to do is I'm going to look at each state in here. I'm going to see what states I transition to on this given symbol. So 0, then I'll also look at 1. And I'm going to just collect all of those states up by performing a union on each to get one superstate. So I have Q0. If I look at Q0 and I read a 0, what do I get? 0, the only one is here is it keeps me in Q0, so I just write Q0 like this. And when I read a 1, I get Q0 or Q1, right? It could transition to Q0 or Q1. Like so. Okay, how about on Q1? When I read a 0 on Q1, where does it go? Somebody tell me. Where does it go when I read a 0 on Q1? It goes Q2, perfect. Perfect. And because there's no transition on Q1 with a 1, it's going to go to our dead state. Because there's nothing to transition here, right? Remember in delta, if you look at the actual transition table for this NFA, it would have an empty set right there. But hence there's nothing to union it with because there is no transitions anywhere on that one state. Now Q2 is actually really easy. There's no 0 or 1 leaving this, right? So you know they're really easy. I want to really work on these ones because these are where things get interesting. Okay, Q0, Q1. Okay, when I read Q0 and Q1, what I do is I look at what happens when I have symbol 0. So on Q0, I would transition with the NFA to Q0, right? If I'm in Q1, where do I transition? I transition to Q2. Are those all the states? Those should be all the states. If I were to look at this one, I look at the transition, and I look at this one, I do the transition on 0. So I take those, I union them together, and end up with Q0, Q2. So all I do is I look at what this transitions to on 0. I look at what this does when it transitions on 0. I take the union of all their results. This applies no matter how many states you have. You just look at each one, you do the transition, you just lump all the states that could go into one set, and that's the label you're going to give for that transition. Okay, so 1. Now 1, let's see. So if I read a 1 on Q0, it could go to Q0 or Q1, right? So, and on this, there's nothing going to 1 here, so that's empty, right? However, it's the union of the results of those two things. So it's just simply Q0, Q1. Okay, now Q0, Q2. Okay, so if I read a 0 on Q0, I get Q0. I read nothing. I read a 0 on Q2. It goes nowhere, right? So this is just going to be Q0 right here. Is everybody getting the idea? So all I'm doing is I apply the transition function for each one of the listed states here, and I just lump together all of the states that they could transition to on that symbol. That's all it is. So likewise, Q0, Q2, if I read a 1, notice that I could go to Q0 or Q1. But on Q2, I don't go anywhere, right? So this is going to just be Q0, Q1 again. Q0, Q1. Okay, 1 and 2, 1 and 2. Is everybody getting the idea? So all I'm doing is I read the transition function for the NFA. I see what states I go to. I lump together all of them for that given input symbol. So I just read what this says. I go through each one. I apply the transition function on the NFA, and I see what states I could gather up. And I collect them up, and that's what I put over here. Okay, so Q1 and Q2. Okay, if I read a 0 on Q1, I go to Q2, right? But I don't have any transitions out of Q2, so this better be just Q2. There is no 1 leaving Q1. Neither is there 1 for Q0, so you know that's just going there. Okay, I want some help with these last two here. Could somebody tell me what should go right here? Yeah, Q0, Q2, perfect. Perfect. Now Q0, Q2, and how about this one? Perfect, perfect, that's exactly it. Is everybody getting the idea of this? It's important because we're going to see another subset construction variant on this later on in this course, and it's going to build on top of this one. And also going to see a simpler version of this, actually right now. So does everybody see how this works? So now I've labeled all the start state, the final states, I have the transitions. Now it's about drawing the picture. Now, of course, if you really just feel you don't really like these labels, what you could do is you could relabel all of them. So for example, I can take all of these, 0, 1, I can label them with letters, for example. Now, I'm just going to copy this down. I'm not going to walk us through this too carefully. So I'm just going to, instead of labeling them as these things, because remember, I told you they're just labels. So if you don't like these, you could just use different names for them. D, E, F, G, and H. So I think it's these last 3 here. Then D, I think, is a final state. And then B is a start state. A, B, E, D, A, F, E, B, E, D, A, F, E. So this is an equivalent transition table if you don't really like those labels of these guys over here. And here's the great part, is that you can draw, of course, a transition diagram for this. I'm going to leave drawing the entire transition diagram to you as an exercise. I'm going to draw the part that's only reachable from the start state. Because you're going to find out that, like I said, this procedure can create a lot of junk. And I mean, like, it's stuff that the DFA will never use. So this is what the resulting DFA would look like if you deleted or discarded all the states that are not accessible from the start state. So this is what the resulting DFA would look like if you were to just discard all the extra junk states. They don't go anywhere. Is everybody okay with that? So we're going to now, because I've described this entire process to you, note that there is actually a much easier way of doing this. You don't have to fill in this entire table. You don't have to discard any of these states or anything like that. You don't get any junk out of the construction. I'm going to show you something called the lazy subset construction. And we'll do an example, and depending on how much time we have, we might start the perf for this equivalence between the NFAs and DFAs. Lazy subset construction. Lazy subset construction. Okay, what I'm going to do is I put more details in the notes if you care to, if you want to read them more carefully, but I'm going to combine 2 ideas. The first one, I'm just going to take this subset construction, And I want you to observe a property that was kind of interesting in its own right when we filled in that table over there. Remember, I told you I only care really about the states that are reachable. And I mean that in a graph theoretic way, or if you don't like that way of thinking about it, I mean accessible, meaning it can never become that state. Anything that is not accessible from the start state is just, may as well just not even be there, as it's not very meaningful for how we use the machine. We're going to use the idea of breadth first search. Now, how many of you have heard of breadth first search? So, or any graph traversal algorithm will suffice. If you don't know, that's okay too. This process is rather straightforward. But I want to just give you the background in case you've never heard of this idea. You might know this as DFS. But you can think about this as just any old graph traversal algorithm that you would use on a directed graph. What I'm going to do is we want only states reachable from the start state. From the start state. I'm going to define something we're going to call discovered. This is just to make it easier for you to know. This is not something you need to know specifically about this construction. I just find it's easier to learn the lazy subset construction if you have this notion. Okay. We will call any state where we have not written a row for it in the transition table. Transition table discovered. I'm going to call it discovered. So I'm going to write this in terms of the transition table. You'll find it's a little easier to think about if you think about the transition table. However, there is a natural graph theoretic way of thinking about this exact process. It's exactly breadth first search. What we're going to do is, there's two steps. It's really this simple. Begin with the start state. Begin with the start state Q0 of D. It is discovered. I'm just going to declare that it's discovered. So that's the first step. The second step, this is going to amount to a loop, if you were to write this out in actual code. While there is a discovered state, I recommend examining in the order discovered, but you don't have to. It just makes it a little easier to keep track of things. If you examine them in the order you discover them, you can think of this, if you're thinking more algorithmically, you think of it as a queue. Hence my idea of breadth first search here. You're going to add a new row, for it in the transition table. Where its transitions are described by the subset, described in the subset construction. So all I'm going to do is I'm going to start off in the start state. My new start state I create for the DFA. I label that as discovered. And while there's a discovered state, I'm just going to add a new row to the transition table for it. And I'm going to complete its transitions in the table, in that row. And if I see a new state I've discovered, I declare it as discovered. And while one of these exists, you're going to keep doing number 2 here. And that's it. So I'm going to do one example here with you. And I assure you, it's going to go pretty fast. So I'm just going to remind you what the picture looked like. Actually, let me do it over there. Let me do it over there just to re-emphasize this. Because we have just enough time to do this example. I've included more examples in the notes. So if you really just find yourself, Dan, I don't really get this, there are more examples in the notes. Be rest assured. Because I wanted to make sure you had plenty of examples to fiddle around with. So just keep in mind this picture of how big this transition table was. Okay. So I'm going to build the transition table like I did before. I'm going to start off with Q0. I'm going to use the exact same picture I did before of an NFA. I'm going to build it using the exact same NFA so you can see that we're going to end up with the exact same result that we had before. Now Q0 is indeed the start state. So Q0 with the subset, right? And I'm just going to do the process again. So remember, on 0, Q0 just goes to Q0. And then I see on 1, I could go to Q0 or Q1, right? Now, I've already discovered Q0, right? By writing out its transitions, I'm done with it. But notice I've discovered a brand new state, this one. So what I'm going to do is I'm going to write a row for Q0, Q1, because I haven't yet, I'm just going to label it as discovered, because it's not like, I haven't done that one yet. Q0 has already been done. It has a row for it. So I just look in the row. So I have Q0, Q1. Now, just for the sake of time, I'll just write out Q0, Q2. We already determined this. Actually, we had our own row with this. Like any of the rows that we had before, they're going to be the exact same in this process. Just I'm going to avoid all of those junk states that we don't need, that you just discard. Q0, Q1, like this. Okay, so notice that Q0, Q1's right here. However, notice that I just discovered a brand new state. This is not in our table yet. You don't see it over here. So I'm going to proceed to process that one's transitions. Now remember, it contains Q2, so it isn't going to be indeed a final state. When I read a Q0 or Q2, I look at this one. Okay, well, 0 on a Q0, that goes to Q0. Q2 on nothing, it's just going to be Q0 here. And on a 1, it's just Q0, Q1. Do you see any states that I have not accounted for in this table? So every one that appears here has its own row, right? So I have not discovered any new states, hence I'm done. Do you see how much faster this is to do? And now this is the fun part. I kind of erased a little bit of it. Actually, let me just redraw it. I'll let you keep that in mind. Just because you should see one of these with even the states labeled. So I'm going to have 3 states, one for each of the rows. So I have Q0. This is the start state. It goes to Q0 on a 0. It goes to Q0, Q1 on a 1. On a 1. And on Q0, Q1, it goes to Q0, Q2 on a 0. And it goes to, on a 1, it goes to itself. And then I have Q0, Q2. This is a final state, right? And then, let's see. It tells me to go to Q0 on a 0. And it goes to Q0, Q1 on a 1. Bam! Notice it's the exact same transition diagram, right? It's just I didn't make the labels different. See, notice that there's no other rows in this. So the lazy subset construction, you could use this to ensure that you're only going to account for the reachable states. And this has a natural intuition with a graph traversal algorithm. The reason why I call it breadth first search is because I'm looking at the rows as I discover them. However, you're not required to do this. If you wanted to take more of a depth first search approach, you could do that with this process and it'd be perfectly fine. The only difference here is that it makes it easier to keep track of, because you'll notice that whenever I discover a new one, it's going to be in some row I've already examined. But it's like within the order I could read them. So for example, I picked Q0, Q1 because this is the first state I haven't yet accounted for. It's been discovered. However, if I add more of them, it's easier to keep track of them, as you could read them from top to bottom, left to right, if you do it this way. Is that clear, everybody? So this is the lazy subset construction. So I have a couple more examples in the notes. Next time when we come back, we'll prove the equivalency of NFAs and DFAs. Is that neat? So that being said, I'm going to wrap things up here, and I apologize for taking a few of your extra minutes. I apologize. So that being said, I say thank you very much, and have yourself a beautiful day. I'll see you later.